A little while back, I nerd-sniped myself into trying to make a spatial audio system, and this is an overview of how it works. Caveat, it's not that great, but I think I learned enough to make a better one in the future. Before we go into it, let's just listen to an example. Okay, so that's kind of what it sounds like. As you can hear, it has some issues, but it does the basics of the thing. So here's how it's built up. Spatial audio is really all about making sounds that are mono sources placed somewhere in like a simulated space sound like they're in a real space. And so there's 5 kinds of effects that I've tried to model. There's attenuation, so high frequencies dissipate quickly over distances. This is why if you hear a concert in the distance, it sounds very bassy. There's reverb, so that's like the sustain of sound as it bounces around in an environment, like how it echoes in a tunnel. There's occlusion, so when you walk behind an obstacle, the sound should get weaker. There's reflections, so that would be echoes, and also the really short echoes that give you a sense of the space that you're currently in. And there's spatialization, so that's simulating how the ear affects the sound, and that makes the sound like it's coming from outside of your own head. And before we sort of go into them, let's just look at the what is a sound. So if you play a loud click in an environment and you record the result, you get something called an impulse response, and it has a certain structure. So it has this main sound that arrives at the microphone after traveling directly to it. Then you're going to see some like early reflections, which is the click distinctly bouncing off of stuff that's nearby, and they're going to be weaker than the direct sound, but sort of still distinctly a click. And then you get the late reverberations, which is sort of the very diffuse bouncing after it's bounced around a whole lot and really spread out, and that's sort of the softer, longer tail of the sound. So if you map those onto the concepts that I looked at before, right, they're all subject to attenuation because they all involve traveling through the air. But for the reflections, we need the reflections, and for the reverb, you could do that with reflections, but you'd need a whole ton of them, so it's easier to do that by directly mapping it with a reverb effect. So to do this, I had to implement a couple of different parts here in orange on the right. There's a need for an equalizer to change the amounts of different frequencies. We need some kind of sound traveling simulation for both occlusion and reflections. We need a reverb filter, and we need to be able to parameterize it to fit the room that we're currently in. And to simulate the ear, we need something called a head-related transfer function, which is a special filter you apply to the sound. And then finally, to tie all of this together, I made use of something called ambisonic sounds, which is a really helpful tool in spatial lighting audio. So let's look at all the parts one by one. A head-related transfer function is an audio filter that you might apply with a, well, it's a convolution filter. It's an impulse response recorded by taking a dummy head, putting it in a room with microphones in each ear, and then you play a sound from all around the head and measure the impulse response of that sound in each ear. Because the head shape, the outer ear shape, and the upper torso shape affect the way that the sound reaches your head, and your brain has learned to process that change, and from the effect in the left and right ear infer where the sound came from. This can even let you distinguish between like sounds ahead of you and behind you These are convolution filters, and they're typically pretty small, like 128, 256 samples long. But convolutions are still really expensive operations because you have to, well, you sort of slide two signals along each other, and you have to look at the whole overlapping part for every possible way you can slide them together. So for long signals, that's a costly thing to compute, so you don't want to do this too much. But it's very doable. And HRTFs are available as libraries of these left and right impulse responses, and you get one for each sort of spatial direction. And then when you want to spatialize a sound, you would find the one that you need and apply it to the signal, and you get your left and right signal that you can mix together. A super useful tool is ambisonic sounds. So ambisonic sounds store sound as a spherical harmonic. So what does that mean? Spherical harmonics is like a function on a sphere that encodes, it encodes both the direction and effect, right? So when you store a sound on a sphere, you get to store both what the sound is, but also what direction it's coming from. And you can store multiple sounds from multiple different directions in one set of ambisonics. Spherical harmonic comes in different orders with increasing number of channels, but I used the simple 4-channel representation, second order, I think, which really has 4 sounds of sound. So there's an omnidirectional one, an X, a Y, and a Z. It's really simple to map a sound and a direction into the ambisonic. You just use the direction vector that the sound is coming from. You add some normalization constants, and then you multiply the signal with that, with each channel's normalization constants, which is really just the, proportional to the direction. It becomes a bit harder with the higher order ones, but it's still not very tricky. And then the thing you can do is, for one thing, you can store multiple sounds from multiple directions in one set of channels. The other thing you can do is you can rotate it, and this comes in very handy. So for this 4-component representation, it's the same as just rotating a vector, right? The omnidirectional one stays the same. The other 3 rotate much like you would rotate a vector. And this has the exact same effect, as in it will rotate the direction that the sounds are perceived to be coming from. So how do you play this in a way that makes it useful? Well, you could have a speaker array all around you, but you can make a special head-related transfer function that takes ambisonic sound channels and transforms. It would have then, in this case, you would have 4 filters for the left ear and 4 for the right ear, 1 for each channel of the ambisonic, to make a spatialized sound directly from the ambisonic. And you can generate these special HRTFs with a whole category of different methods. It's a genre of scientific papers, but I used one called MagLS, magnitude least squares. And the simplest thing is to go to a package like SP Audio Pi to compute them. When you have the great advantage of doing it this way is that instead of now needing to have an HRTF for each direction a sound could be coming from and applying it per sound with its direction, you have a single set of impulse responses, a single HRTF for the ambisonic in one way that produces your left and right spatialized sound, and then you can rotate the signal in the ambisonic. You can rotate the ambisonic and feed it into the HRTF to get the result for a rotated listener. So you never have to have multiple HRTFs and blend between them. You can just directly, rotate the signal instead of rotating the HRTF, and that simplifies the setup a whole lot. It also has some sort of potential benefits in terms of performance. If you have, in this case, more than 4 sounds, you would need to do 1 convolution per sound or 2 convolutions per sound. So that would, whereas in this case, you just do 2 convolutions per channel. So if you have a lot of sounds playing, it becomes more efficient to do it this way as well. For the equalizer, I used something called the Linkwitz-Riley filter, and this is the part that I probably understand the least about. Or it's, to me, a relatively magical way of, with a single number of state, separating a signal into a low and a high version, or really you're not separating into a low and high, you're getting one of them. But the trick with the Linkwitz-Riley filter is that it perfectly adds to one, so you can, if you added your low and high back together, you get a perfect original signal back. So the neat thing is you can use multiple filters to make multiple bands, because you can subtract the results of one from another to get like just an intermediate band. Then of course, right, for the equalizer, since we're going to use it for attenuation, we just set the gain of each band by the distance. So I've set it up to use 4 different bands, so like a low, a mid-low, a mid-high, and a high. And then we just set it so that the farther away you are, the more you tune out the high ones. The thing I don't like very much about this effect is that I think the default LR2 filter that I used just doesn't cut off the sounds quickly enough by frequency. Like even if you remove everything but the lowest band, you still get a fair amount of highs left in the signal. Control of the frequency band's perspective. But there are higher order versions that I think store a little bit more state. With those, you could get much finer control. Although maybe my implementation is wrong. For sound travel simulation, I made a little raycaster. The exact details of how ray tracing works is beyond this, right? But you could use whatever's in your physics engine, or, well, it's used for both occlusion and reflection. So first off, occlusion, I went with a bidirectional trace. So you trace from the listener to the source and from the source to the listener. And then, of course, if there's no obstruction, you just get the full distance for both of them. But if there is an obstruction, you can very easily use the position of the intersections and the source and the ear to compute how much of the distance is obstructed, and use that to choose how much to attenuate the signal. And the nice thing about that is, if you think about the source moving here, when your asset approaches the corner, the amount of occlusion is going to become less and less, so it sort of naturally fades out as you move around an obstacle, which just like a yes-no raycast wouldn't do. For echoes, the idea I had was that if you sort of mix too many sounds together, you tend to get strange effects on the sound that are sort of unpleasant. I figured let's try to keep it simple with one echo per cardinal direction. And so the listener throws out a bunch of rays to generate these echo points around it in the space that an echo could be coming from. And then each source raycasts to each of those echo locations, and if they're unobstructed, the distance for that, the total travel distance to get to the echo point and to the listener, as well as the sort of strength, which is related to like how nicely are you bouncing, right? You want to have a nice incident exit angle that matches to get a strong bounce. That strength and the distance is encoded first in like a per direction number, and then ultimately the distance and magnitude per cardinal direction is used to write it into the ambisonic representation. So in this case, for example, right, we're going to have a later echo from these 3 points up top that's stronger because there's more of them. And then we're going to have a weaker echo, but closer to the main signal from below because of this one coming in here, right? Echoes end up having a little bit of there's a tricky bit of implementation that I didn't foresee while writing them. So you actually need to simulate speed of sound travel through the air and the Doppler effect to be able to do echoes for continuous sounds with moving sources or a moving listener. The reason why is, if you think about moving listener here, for example, that moves at frame at t0, it moves a little bit closer at t1. The delay that it's going to want to hear the sound at changes between these 2 points. So if you think about what part of the sound that it's playing at each frame, it's going to start at frame 0, play some interval that, the length of the frame, and then the offset is going to have to change. So it's going to have to change the offset and then keep playing. That change in offset creates an audible pop every time. It sounds very bad. So you need to somehow get rid of this, right? Like what you want to do, and the way you want to solve this is by saying, well, for my second frame here, I'm just going to start playing exactly where I left off, but play the sound faster so I catch up to where I want to be. playing the sound faster to catch up to where you want to be in relation to movement, that's the Doppler effect. So you're going to need to implement Doppler effect, whether you want to or not. But it's nice, right? It's a cool effect that you might want anyway. Fortunately, this is fairly straightforward to do for like small changes, because you can just linearly interpolate. You can simply, right, if you have this signal in red and you want to sample it, you want to play it at a faster rate, you can just figure out where your new sample should go and linearly interpolate the original signal to get the result, and it sounds pretty okay. You can do nicer reconstructions, but lerping seems fine. And then, if you don't want Doppler and speed of sound on the main signal, you could feasibly like always treat it as being at distance 0 and just subtract off the delay for the main sound, and just only think about the distance to the echo and then play the echoes. But you're still going to need the Doppler on the echoes because the distance is going to change as you move. So yeah, you don't get away without doing a Doppler effect. You need to be able to resample your sound at non-integer coordinates that change over time, or it doesn't work. What about the sound travel that I don't like is the echoes didn't turn out that good. I don't know if the cardinal direction or is too coarse of a representation to do it well, or if it doesn't transfer well into the spherical harmonic somehow. Or maybe echo effects are supposed to feel really weak, and I'm just expecting more than I should. The Doppler effect, on the other hand, feels too strong. I don't know if this is because the brain notices when you move in reality and like compensates, because I've never felt like I hear Doppler effects from moving past the speaker at walking speed. Maybe the walking speed in my simulation is a little high, but still the effect seems quite strong to me. Finally, the occlusion, it's a little bit disappointing, right? So in reality, sound, because it's a wave, sound really likes to go around corners, right? It doesn't just go to a wall, penetrate through to some extent and then continue to the ear. It actually travels around the length of the wall, and it bends really well around obstacles. And so in reality, when you hear a sound that's occluded, the direction the sound should be perceived to come from is some combination of the transmitted sound and the sound that traveled around the obstacle, right? One way that people have tried to resolve this is by using pathfinding to say, well, what is the path the sound is going to travel, right? So you pathfind from your ear to your, from your source to your listener. You find the shortest path, and you use that direction and that length to tune the sound. But then you run into sort of discontinuity problems where what if between, what if you move a tiny bit but the shortest path changes drastically? That's going to produce a pretty uncomfortable change in direction that doesn't feel right. So I don't really like that solution. The other thing that you can do is you can just ray trace ray trace with reflections much more deeply than what I do, right? So what if you allow for like 10 bounces? Then things are going to be able to travel, between rooms and down a corridor and whatever, because it's just going to bounce over and over. But that doesn't work if you have open areas. So like if you're outside and there's only open sky above and there's a wall in front of you, you should still hear someone on the other side of the wall, both because of transmission, but also because the sound goes around the wall over it. But there's no way for the rays to bounce over the wall because there's only the sky. So that feels unsatisfactory too. I feel like the solution here involves some kind of like wavefront propagation simulation. But to do that in a way that's going to be fast and consistent enough seems pretty tricky. Finally, the reverb. For the reverb, I relied pretty heavily on this excellent article by Geranlov, Let's Write a Reverb. Strongly recommend reading it if you want to write a reverb. The way that it basically works, like a reverb is this long sustained echo that keeps going, right? So to do that, we want to have a feedback buffer where we stick sound in, we keep playing it over time with some delay, and over time we sort of fade the signal in there, right? and we can stick more sound in when more sound arrives. But that's going to produce like a delay echo, right? So you're just going to get like a bup, 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 with a very distinct repeating sound, and we want to avoid that for a reverb, which is more continuous and spread out. So to get it continuous and spread out, there's two tricks, right? So one is to not have one of these feedback delays, but to have multiple ones with different delays on them, and then we sort of mix the outputs from all of them into the other ones, so that the sound gets repeated at a bunch of different delays, which helps remove any noticeable rhythm. And then the other thing is that before we even stick the sound into the delay buffer, this feedback buffer in the first place, we want to pass it through a diffuser that turns it from like a sharp echo, like a tick, into a little sort of very dense package of signals, like a shoop. That's going to be more spread out from the start, so it's going to further reduce any individual sharp sounds that we can hear. That works basically the same way. It just uses shorter delay, but we pass it through a delay filter. We split the signal into multiple ones. We pass them all through different delay filters. We mix them up, and then we keep doing that over and over. There's just no feedback. It only goes through once to produce one diffused sound. Yeah, I mean, if we quickly look at the code, that's basically what it does, right? The diffuser runs for multiple rounds where we pass it through a delay, and then we sort of shuffle and mix them up. And we do that over and over. And then that diffused signal is fed into the feedback where, well, we keep playing it over and over, and we have this gain parameter that says how quickly does it decay in there. This is the thing that we adjust to match the room. And then finally, after that, we can blend all the channels together to get a final output. But I really recommend referring back to this Let's Write a Reverb article if you want to know much better than what I can explain how to make a reverb. The other thing that I found really useful here is there's a bunch of numbers that you have to pick, right? Like the delays, how you shuffle the signal. Well, those are the main two things, right? What delays are you picking? I think a reasonable choice is to pick prime numbers, because when you have these things that are supposed to repeat over time but not overlap or interact with one another, prime numbers have this guarantee that you always sort of go through all the other options before you land back where you were. So picking primes seems reasonable. But I don't know if it's really necessary. Either way, what I did was I implemented this whole filter first in Python. I randomly selected the delays over and over until I arrived at something that sounded nice, and then I encoded it into my main program, and that worked really well. And then to parameterize it, right, the idea I had was to get a strong reverb, you want to have parallel walls that things can bounce off of, because you need the sound to like bounce around a bunch. So for it to bounce around, it needs to be able to bounce, in one direction and then in the other direction and back and forth. So it just does a bunch of paired raycasts in each direction and looks at the distance between them. And you don't want that to trail off to, like if it trails off to infinity in one direction, right, then you don't get any reverb, whereas if it's shorter, you do. And I'm sure you could parameterize it better, but I think it's a reasonable choice, maybe. The reverb sounds okay, I guess. I'm not entirely happy with it. Like, I don't think one parameter is really enough to capture all kinds of reverbs, right? Like a concert hall sounds different from an underground, cavern or something, even though they're both really reverby. Like a concrete corridor has this really harsh sound. And it would seem to me that you need more things to tune in the reverb to really make it sound correct in all scenarios. The other thing is there's this effect with noise, I guess, and with signals. Like reverb is kind of a noisy signal in the first place, where if you have uncorrelated signals for the left and right ears, it sounds a lot better. Sounds a lot more like you're in an open space. You can hear this very clearly if you play a white noise signal, either the same signal into both ears or a different signal for left and right. It's very obvious that the different signals sounds like you're in open space, kind of. And I think this is a very nice impression to be, like a nice effect to get from a reverb. But I didn't manage to find a good way to make uncorrelated signals. Like if you try to mess up try to like change, like have two reverbs with different diffuse, like different delays in them, for example, it's really hard to get them to be identical but uncorrelated, right? You always end up with one being slightly having a shorter attack or a longer delay or something, and it's really hard to tune. But if there was a nice way to get uncorrelated reverb, I think that would be really helpful. And I'm not sure how that interacts with the ambisonic encoding. Like, do you need 4 uncorrelated signals, 1 per ambisonic? I'm not sure. The other thing is, I do think you need to apply reverb per sound, ideally. Because if you imagine you're outside listening to someone in a large echoey building, that should sound echoey because they're in an echoey building. But if you're in the echoey building and they're outside and you hear them, it should still sound echoey because you're in a large echoey building. So like you should parameterize it on like the sum or maximum reverb of either you and the source. And that requires you, of course, to do a reverb per sound that's playing, which could get a bit costly performance-wise. And then the other thing is you probably want to like... reverb is sort of a long-lasting slow effects. So you probably want to let the parameterization change slowly over time. If it changes very sharply, it sounds a little strange, I find. But that's an easy fix to do. One more thing for parameterization. Maybe it's worth taking the normal of the hit surfaces into account, right? Like you have these parallel walls and they bounce right back to you, so that's a very long reverb. But if they're orthogonal, maybe they just, you could assume that they go away and it's not a strong reverb. I don't know if that's a good heuristic or not, but maybe. So that's all the parts that went into my simulation. On the whole, I'm still reasonably pleased with how it turned out. Like, if I fixed up all the errors in this, I don't think it would sound terrible, but I do think it's possible to do it better. And of course, right, like if you actually need a spatial audio solution for a thing you're making, like maybe check out Steam Audio or something instead. I don't really know if it's worth writing on your own, but it's an interesting project and fun to play with.